Gas exchange. There's gas exchange is going to be happening in two places. Gas exchange is going to occur within the lungs. A gas exchange is going to occur in the capillary bed with the tissues. So when it comes to those two things, they're going to be dependent upon really a partial pressure gradient going from high to low. Guys, let's think of partial pressure gradients as concentration gradients, okay? Because for all intents and purposes, it is the exact same thing for us, all right? It's going to go from high to low. All right? So when it comes to gas exchange, it's really going to be based on going from high concentration to low concentration, or going from a high partial pressure gradient to a low partial pressure gradient. And just close your eyes, right? Close your eyes. Think about this. When you are exhaling, we are exhaling to get rid of all of the carbon dioxide that we've accumulated in our body, right? So wouldn't it stand to reason that we would have a high amount of carbon dioxide in our body compared to the outside? Yes. So it'll go easily from the blood to the alveoli and out to the environment. In the same vein, think of oxygen now. Oxygen is much higher concentration outside in the atmosphere compared to in our lungs. So it's going to go from high to low. Getting all that air into the alveoli, yes, still atmosphere, and getting it to cross that very thin barrier to easily get into the blood. Okay, so all of these gases are going to be going down their partial pressure gradient. Dalton's law talks about partial pressure and the pressure that is that pressure that gas exerts on a membrane. When we look at the partial pressure of atmosphere, it's equal to all of the gases within the mixture. Oxygen and carbon dioxide are going to be the primary ones. But we have a lot of other minor gases. There's water vapor, there's nitrogen, and then there's a bunch of small other ones as well. All right. Totality together, all of that equals 100%. All of that equals 760. Okay. But we are just going to be looking at basically these two. We may reference carbon monoxide, okay, when we talk about, but on an exam, I'm really only asking about carbon dioxide and oxygen, because those are the two primary gases that we are concerned about with transportation, okay? And carbon monoxide isn't normal, unless you want to try to go sit around a combustion engine for a long time. Don't do that, okay? Don't do that. All right, this is what I just said. This is what I just said. We have two types of gas exchange that we will be talking about. We've already talked about one, right? We already talked about really systemic gas exchange earlier, but now we're looking at who's actually holding on, okay? Yes, it's a red blood cell. Yes, it's hemoglobin, but it's a very complex structure, and we actually have different parts of that complex structure that hold on to oxygen or hold on to carbon dioxide, okay? And these are going to be, and this red blood cell structure, this hemoglobin structure, it has some unique characteristics about it that makes it want to hold on to oxygen so damn fast in the beginning, and a lot. And then by the time towards the end of this loading of hemoglobin molecule of oxygen, it's like, done, man, done. And then there's a number of things that are either in a red blood cell or in the surrounding tissues because of enzymatic reactions or metabolic reactions that make it so oxygen jumps off very easily, and it makes it easy for carbon dioxide to be absorbed in the blood with the red blood cell. So we're going to be looking at the various different reasons why red blood cells hold oxygen or hold carbon dioxide, or blood holds carbon dioxide very easily, okay? And part of it is these partial pressure gradients. So we have alveolar gas exchange, which I imagine you can all tell me right now without studying where it occurs. It occurs in the alveolus. And the systemic gas exchange is going to be occurring within the capillary bed. This is, if you come across some old school names, this is old school external and internal respiration. But they got rid of those terms, I think, just this past year. So if you have an old textbook lying around for some crazy reason, or if you search something on the internet, when they talk about internal and external respiration, this is what they're talking about. Internal is systemic gas exchange. Alveolar gas exchange is external. Okay, so if you do see those written down somewhere else on another website, it is changed. And I will tell you right now, if you go to a site that's more physiology based, you're going to see a lot of old terminology. Okay. So if you see a bunch of words that you're like, what in the hell is going on with these words? That's why. Physiologists give 2 fingers up to the anatomist when it comes to what they name and what they call stuff. Physiologists tend to never deviate. They are very rigid in their terminology, and they don't go away from it. It takes many years to get a change to occur in a physiologist's mind. For whatever reason, I don't know. Okay. But it is, because I teach phys, and it is maddening, the difference between that textbook and your guys' textbook. And it's even more so this semester because this book here that you guys have is based on the new terminology. That one, it's nonsense. Nonsense. All right. So let's get into how stuff moves. To be honest, guys, I don't know how easy. This is the easiest thing that there is when it comes to the respiratory system. Last week, yes, that is not as intuitive. It is not as easy, and I totally get it, and I totally understand it, okay? And you are never alone in that fact. Every semester, since the beginning of time, everybody has issues with trying to visualize inverse relationships and what that means, and it's very hard. Please just kind of look over and over a few times. I had a listing of a few different videos. I'll try and get them up for you so you can see some of that stuff. Okay, but because I have them in some lectures for phys class, so I'll try to pull those over for you guys to see and put some links up in the announcements for you guys there. All right. But the 2 major, or really 4 major, if you look at it, 2 for oxygen, 2 for 2 for carbon dioxide. Okay. We have a partial pressure gradient of oxygen inside the alveolus, which is to say inside the atmosphere or outside in the atmosphere, of 104 millimeters of mercury. If you look in this picture right here, guys, there is a arrow, and it shows you how blood is moving through this tiny little capillary. As it's moving through this tiny little capillary, you can see this has been delivered from the heart. Okay. It comes to that lung in that pulmonary artery. Okay. These are carbon dioxide rich and oxygen poor. When you look at this here, you can see carbon dioxide rich, and oxygen poor. That is not a huge hell of a lot of difference, but that is what happens within the body. You don't ever get rid of 100% of oxygen from the alveolus and load it up onto the red blood cell. You do not ever unload 100% of oxygen into the capillaries. And you do not completely 100% fill your red blood cell with carbon dioxide. There's always a little bit that stays on the red blood cell. Why? Because of some crazy stuff that we'll talk about later, okay? Some affinity, it likes to bind to certain things. CO2 is high within the blood. CO2 is low within the atmosphere. So it goes from high to low, from high to low. Oxygen does the same dang thing. 104 millimeters of mercury. This is huge difference. So because there is a huge difference, what do you think happens really easily? Yeah, oxygen comes in really easily, right? This is a huge, steep gradient here. Okay. And carbon dioxide, it's not as steep. Okay. It is not as steep. But still, from high to low occurs. It is the exact opposite within the capillaries. It is the exact opposite within the systems. Here I have another arrow showing you blood flow, okay, going from the arterial side to the venous side. As the blood reaches, it starts out as this, okay, and then comes down here. Okay. This oxygen molecule, as you can kind of see, has been giving up some O's, giving up some oxygen. As we get deeper into that capillary bed, we have a high concentration here of oxygen, and we have a low concentration within cells of oxygen. What are the cells doing? The cells are doing metabolism, right? They're doing metabolic activities. What helps to drive that? Oxygen helps to drive that, right? So as this oxygen enters, it's going to be utilized. So this, again, is a pretty steep difference. Excuse me. So it goes easily from the red blood cell into the tissues. What's been accumulating within the tissues, within the cells? Carbon dioxide, right? Carbon dioxide, hydrogen. Those are some of the byproducts of metabolism that we looked at way back at the beginning. So as oxygen unloads, this is going to increase the affinity for carbon dioxide to want to load up onto Mr. Red Blood Cell here. Carbon dioxide enters into the blood and gets picked up by the red blood cell, and we are exactly the same as we are up here when the heart pumped this carbon dioxide rich and oxygen poor cell towards the lungs to pick up more oxygen and drop off carbon dioxide. Is everybody with me there on that?
Yeah.
Okay. All right. Something that we need to talk about is temperature, because temperature is generally constant. All right. Carbon dioxide. Breathing, you never go generally from one big extreme to another, unless I guess you're somewhere where it's really, really, really cold below zero and you go outside, or you're inside and it's really, really hot. Let's say you've got the thermostat set at 75 degrees, whatever. And then you go outside and it's like 30 below. So I guess, there are major swings that can happen in certain locations. But generally, temperature is relatively similar. When that's the case, and that's what we're kind of talking about here, when temperature is generally similar, it makes it easy for gas to get where it wants to. Okay. So under normal everyday circumstances, you're bebopping around your house. You are walking out to the car, running errands, normal daily activities. This is constant. When you get a change in a big change in temperature, you decrease the ability for gas to get from one structure to another structure, because you're now affecting the solubility. Think of it this way. Close your eyes. Think of it this way. When you are exercising, what happens into a muscle? What happens in a muscle? Okay, anybody think?
Flex.
What'd you say?
Lactic acid builds up.
Sure. But before that, what happens?
Contraction.
Contraction. Okay. After that, what happens? You guys have all exercised before, yes? Did you get cold? Did you get hot?
Get hot and you need more oxygen.
You get hot, right? That hot is equated to work, right? Potential energy to kinetic energy, work. Muscles contracting. What does a muscle need to maintain that activity level, that increase in activity level? What does it need? I think Imelda said it.
Energy.
Energy. How do you make energy? What do you make energy from?
ATP.
Okay, how do you get ATP?
With mitochondria.
Mitochondria. What do mitochondria utilize? For mitochondria to do their work, what do they need?
Oxygen.
Oxygen. Heck yes. Because if there's no oxygen, can I utilize the mitochondria?
No.
No. So if I get an increase in heat, I get an increase in metabolic activity. Got an increase in metabolic activity because I got an increased work. I'm doing more work. I'm contracting. Don't necessarily have a buildup of lactic acid yet. I'm not doing high intensity stuff. Okay. But I'm exercising. Muscles increase in temperature. Why? Heat is a byproduct, right, of metabolism. Because the transfer of energy from one form to the next is never 100%, right? You always give off some of that as heat. As you increase the heat within a muscle, you're also increasing the amount of oxygen that you're utilizing. This makes it so oxygen easily wants to disassociate from a red blood cell and get into where it's needed. This also helps to change the solubility of carbon dioxide. Carbon dioxide is being produced copious amount within the cells because of this increase in metabolic activity. So now it's going to want to get into the blood even more so. Just that little bit of heat is going to increase its solubility factor by a lot. Okay. So if we change a temperature, we can affect solubility of these gases. Okay. Ideally, though, it's always constant under normal circumstances. Okay. Unless you do something different. Exercise is not normal. You guys still see my screen? I had something pop up on my side.
Yes.
Okay.
Yes.
All right. Thank you. Okay. And that's Henry's law. Henry's law allows us to help us to understand gas exchange a little bit more because it talks about solubilities. It looks at partial pressure and it takes into account heat. Okay. How much force does a gas exert on a liquid to dissolve itself? Okay. And CO2 loves to be dissolved in stuff, in liquids. It doesn't take much pressure to force that carbon dioxide into fluids, blood. Oxygen is not easily forced into a fluid. So it wants to get the hell out of Dodge. So oxygen will want to get out of the blood and get into a cell because of that fact. All right. Again, you don't really infuse anything with oxygen very easily. You infuse everything with carbon dioxide to give it that fizz. I think carbon dioxide, what's the number? Carbon dioxide is like 25 times, something like that, 24, somewhere in the 24, 25 range, 24 times more soluble in water than oxygen. So that makes carbon dioxide want to get the heck out of Dodge and get into the fluids. I think then oxygen, nitrogen's soluble in water. That's why if you come up too fast from depths in the ocean when you're scuba diving, you get that nitrogen in your blood, and it doesn't normally do it in very significant amounts. But if you move too fast when you are ascending underwater, it can cause that to be pushed into the blood and prevent oxygen from being bound to the red blood cells as well. So there are a lot of uses for it. So here are all of these individual things that I was talking about with that little picture there 3 slides ago. Okay. You always have 104 millimeters of mercury inside the alveolus. This is constant as you are constantly breathing. For a fraction of a second there, 2 seconds? So as soon as you take that breath, after that 2-second pause, after you exhale, constantly refreshed with more oxygen molecules. So that 140 millimeters of mercury can stay maintained. Okay. The pressure within the alveolus for carbon dioxide is 40 millimeters of mercury. I don't know why that's there, not over here. In that pulmonary capillary, it's 45 millimeters of mercury, so it diffuses from the blood to the alveoli. Again, moving down its partial pressure gradient. And carbon dioxide gets the heck out of Dodge. That is exhaled. And we bring in more every time blood moves through here and everything stays maintained. I'm going to pause and I'm going to share another picture here. There it is. Right there. Oops, wrong button first. Sorry, I want to get to the right slide. Understanding these various different pressures that exist within the lung, or ultimately within the systemic cells, okay, are important because they're on slide, 86? It helps us to understand, and I'll just show this for now. It helps us to understand this concept of ventilation perfusion, okay? It helps us to understand this concept of ventilation perfusion. What is ventilation perfusion? Ventilation is breathing, and perfusion is the concept of how much blood can enter into a region. How can we affect how much oxygen comes into a region? We can affect it by affecting the size of the bronchiole. Okay, remember, the bronchioles are the only things that we can bronchoconstrict or bronchodilate. The primary, the secondary, the tertiary bronchi have cartilaginous rings, cartilaginous plates. Those are there to keep them open. Once we get to the bronchioles, we basically lose that cartilaginous plate. And now it's all smooth muscle that can affect the size of this tube. So these bronchioles are going to be able to affect how much air, oxygen, is getting down into the alveolus. Perfusion is looking at it from the aspect of the pulmonary capillaries. Okay, these things right here. Okay, so I can change the size of the bronchioles, which can affect how much air gets down into the lungs, how much oxygen can get in, and really how much CO2 I can get out, can be affected by changing that bronchiole. If I look at the pulmonary capillaries, I can affect perfusion, how much oxygen I actually absorb in, how much CO2 I can help secrete out. And I can do that by affecting the dilation or constriction, vasoconstriction, vasodilation. Okay. Why is this important? Okay. Why is this important? Because this ventilation perfusion must be matched. Okay. We need to match it. If we don't match it, then I can get too much of a buildup of carbon dioxide within the blood. And what's that going to affect? It's going to affect the pH of the blood. Okay. If I have too much CO2 present within the blood, okay, and I don't have the proper ability to get it out effectively, I get a buildup. So that means I have a greater buildup within the capillaries. Also, if I have an inability to get out a sufficient amount of carbon dioxide, I'm also not able to get as much oxygen in. So what is this going to do to those cells? They're not going to have enough oxygen available. They're not going to be able to do work. They're going to continue to have a buildup of hydrogen ions, carbon dioxide. We get into that lactic acid state, which somebody mentioned earlier. And as we know, the body can't, the cells can't function forever in that lactic acid state. So we have to make sure that enough oxygen and carbon dioxide is getting in and getting out respectively. And the way we do that is by affecting the bronchial diameter and the pulmonary capillary diameters. Okay. And again, we're looking at these two things. Okay. We're looking at how much oxygen and how much CO2 is in there. Okay. We have a number of various different chemoreceptors all over the body, specifically around the heart, that help to monitor this situation. And I can share these up on Blackboard. Okay. Oxygen level in the blood is going to help control perfusion. Okay. So we're affecting those arterioles, those capillaries. Okay. We want to put capillaries. Okay. Where alveolar oxygen is high, arterioles dilate. Okay. So let's think about this. Where alveolar oxygen is high, so there's a lot of oxygen in the alveolus. Okay. The arterioles want to match that. The arterioles want to match that because they want to bring in all that oxygen. It's not an automatic thing that happens. There's a little bit of delay, that occurs there. All right. So as those arterioles start to adapt to that increase in oxygen, those capillaries, those arterioles start to dilate around that alveolus. I can bring in more blood, and more blood can now pick up more oxygen. I hope that jives with your thinking. Aside from that, as soon as that happens and all of a sudden it's matched, well, bronchoconstriction is going to occur because now it's going to start to decrease because it realizes, oh crap, I've got way too much oxygen in here. The blood isn't keeping up, so I have to do something as well. So the bronchioles will then go through a constriction. to try to limit the amount of oxygen coming in, limit the amount of atmosphere coming in. And this is a balancing act that goes in between. This is homeostasis at its most simplest right here. You get a back and forth with these two concepts of perfusion and ventilation. CO2 is going to control your breathing. Okay. Whoops. When alveolar CO2 is high, bronchioles dilate. So I'm bringing in more atmosphere. Arterioles sense this buildup of CO2. Arterioles are going to constrict. This allows the lungs to eliminate that CO2 a little bit more rapidly. Let's go to a picture here. So up here at the top, let's look at this one right here. If ventilation exceeds perfusion, so if breathing exceeds perfusion, the amount of exchange of oxygen and CO2, okay? So if you pick up the pace of your breathing there, CO2 levels will start to drop and oxygen levels will rise. There you can see what's happening there in this situation. I have bronchodilation. And there's my pulmonary artery, okay, the capillary. It's going to respond by vasodilating, okay, because it wants to bring in more blood here. Remember, this is carbon dioxide rich, okay? So it's going to want to bring in more, but it wants to pick up all that oxygen that's coming in, okay? I want to pick up all that oxygen that's bringing in here and get it in. The high level of oxygen that was being delivered here, the body's like, oh crap, I have a buildup of oxygen. I need to get that out and into the red blood cells, into the system. So we get that vasodilation to help pick up the oxygen. While it's doing that to balance out what's going on in here, the bronchiole, as you can kind of see, went from being big and fat to now being skinny. This is bronchoconstriction. Even though you've picked up your pace in your breathing, I can affect how much atmosphere gets down here and limit that. So it bronchoconstricts to limit the amount of oxygen coming down in here. This allows, ultimately, for CO2 levels to rise in the blood, because what is this doing down here? I've increased metabolic demand because of the stress on the body. Oxygen's going to get in. Cells are doing more work because they are stressed. And CO2 levels can rise back up. If too much blood is being delivered, okay? If too much blood is being delivered to the lungs, carbon dioxide rich, oxygen poor, right? And I have bronchoconstriction going on in here. Now I have perfusion exceeding ventilation. Too much blood is coming in, not enough air is coming down. So I'm getting a massive buildup in CO2 here. I vasoconstricted what was high out in the atmosphere, oxygen. So oxygen levels will start to diminish. The way the lungs fix that is going through bronchodilation, right? They bronchodilate there. They've gotten bigger. This can bring in more atmosphere, which is bringing in more oxygen. To limit the amount of CO2 here, I can vasoconstrict. So I can slow this delivery of the buildup of CO2 here until these two things can balance out. The purpose of this slide right here, at least these two things right here, help us to understand how much effect oxygen and CO2 levels have, not only at the systemic level, but here at the pulmonary level. How much oxygen, how much CO2 we have, okay, present within the lungs or present within the pulmonary circulation will affect one and the other. Okay. This is a fantastic slide right here. This, I don't believe I have in your notes. I'll put it up on Blackboard. Okay. Just by looking at this slide here allows you to really get a sense of this concept of ventilation perfusion.
Sometimes can you go over it again?
I'm going to mute. You can type what you want to say as well. It didn't come through.
Oh, okay. Can you hear me now?
Go ahead.
Okay. I said, please, can you go over this again? Please.
Did you say go over it again?
Yes.
Ah. All right. I'm going to there's some stuff getting in my way. I couldn't see a few things. All right, so here, in this situation right here, okay, it won't let me. I don't think I can. No, I'm just gonna have to suffer. All right, because I need my pen. All right, so right here, in this situation, breathing in way too much oxygen. Okay. I have bronchodilation. So if I have a high amount of bronchodilation, I'm bringing in a hell of a lot more atmosphere. And what am I essentially bringing in a heck of a lot more of? Oxygen, right? Because oxygen was way high on the outside than anywhere else, than any other of the gases. So oxygen level is high. The pulmonary artery is vasoconstricted. Okay. For whatever reason, I have a little amount of blood being delivered here. The only way to get this oxygen here into here is to vasodilate, okay? So this arterial here will undergo vasodilation, right? To help bring more blood here to pick up or to offload, however you want to look at it, to pick up more oxygen. So this helps to balance oxygen concentration gradients. If we look at CO2, the bronchioles now are going to be affected. With this one here, the bronchioles are going to constrict. Why are they going to constrict? They're going to constrict to try to balance out the oxygen and CO2 levels. Well, if I bronchoconstrict, all right, if I bronchoconstrict, that means I have less air coming down here. So that means less oxygen. Okay. So I'm not going to get a huge buildup of oxygen here. It's going to start to diminish. Two reasons. One, I'm vasodilated. And two, I'm bronchoconstricted, so I've started to limit that. It's also going to allow CO2 levels to rise back up to normal levels. Because if CO2 levels are rising within the alveolus, because remember it's 40 millimeters of mercury, let's say it rises to 43 millimeters of mercury. Blood is coming to it, right? And it's at 45 millimeters of mercury, carbon dioxide is. That's not a very big gradient now. It wasn't to begin with in the first place. Now it's even less. Okay, now it's even less. This is going to allow us to reestablish that gradient that we have, which is what allows oxygen and CO2 to easily go in and out. If I look at the exact opposite situation, where I have too much blood flow coming into the lungs, okay, where perfusion, mark that out again, where perfusion exceeds ventilation, so too much blood, not enough breathing. Okay, so what does that look like? I have some pretty significant bronchoconstriction going on here. So I don't have a lot of atmosphere coming in, and that means I don't have a lot of oxygen. If I don't have a lot of oxygen here, why in God's creation do I have a whole heck of a lot of blood coming here? Because there's a whole lot of blood coming here to dump off CO2 to pick up oxygen, but there's not as much here. So the pulmonary arterioles, pulmonary capillaries, whatever you want to think of it, they're basically the same, are going to undergo vasoconstriction to try to balance out the amount of CO2 being delivered and the amount of oxygen I can ultimately pick up. So as the blood vessels respond with vasoconstriction here, the bronchioles are going to dilate. I have low oxygen levels here. I'm having a buildup of CO2 within it. If I don't have enough oxygen here, I can't do enough. I can't do any work in the system, in the body. So I have to bronchodilate because of this high concentration of CO2 that is occurring here and this very low concentration of oxygen. So we bronchodilate here. So more atmosphere, more oxygen can be delivered inside here. Now I can have a proper diffusion of CO2 from the blood into the alveoli and oxygen from the alveoli into the blood. With ventilation perfusion, what the bronchioles are doing and what the arterioles are doing are two different things. And they're there trying to match each other. One is using it based on how much oxygen is coming on into the blood. Bronchioles dictate their action based upon a buildup of or levels of carbon dioxide.
Thank you, sir.
You are very welcome. Okay. If you know what's going on in the lungs, just tell yourself what happens in the system is exactly opposite. What happens in the capillary is exactly opposite. Okay. Oxygen is now high within the blood. And the tissues have very low levels of oxygen. So it goes from high to low. Okay. It goes from high to low. Carbon dioxide is high within the cells, high within the tissue because it's been doing work. And it goes from high to low. High within the tissues, high within the cells, low within the blood. So it easily goes from the tissue down its concentration gradient into the blood. And then it returns to the lungs and it's the exact same thing. 40 millimeters of mercury of pressure within the red blood cell. For carbon dioxide, 40 millimeters of mercury for oxygen. And then we do the same thing all over again.